Let's look at the amount of force required to submerge a light body when it is taken into a denser fluid. So let's consider a fluid having a density rho and a cube placed in the fluid. The cube has a density rho, let's call it rho 0, the rho of the object, rho O. Okay, so if the density of the object is less than the density of water, we know that the thing that the cube will try to come out. So what is the force required to hold it in this location? So what is the holding force? Let's call it Fh. So let's say this is the coordinate system Z and xy is in this plane. I don't bother about that so much. So if this is the pressure on the lower face, on this particular lower face, the pressure is P at Z. The corresponding pressure from the top is, so this pressure will be P at Z plus delta Z. Okay, let's say this area is A and this height is equal to say it's B. Okay, so this pressure will obviously be pressure at Z plus B. Now if we take a differential element like so, we know that the pressure at Z and the pressure at Z plus delta Z is balanced by the mass of the element. So Pz minus P at Z plus delta Z plus, so this multiplied by the area, let's make it a cube to cause less confusion. This plus area times, if this is delta Z, so area times delta Z is the volume, this multiplied by the density of the object, by the density of, so this is the hydrostatics for the fluid, hydrostatics for fluid. There is no object, this is the fluid in equilibrium at a location Z. Okay, so this is the static equilibrium of fluid. So minus rho A delta Z into G, but G is in the negative direction, so we will make this as minus. So these are the positive forces and this is the negative force. This is equal to 0 in the limit of all volumes shrinking. So Pz minus P at Z plus delta Z is equal to delta Z rho into G. We have cancelled A from both sides, and so we correspondingly get that minus del P del Z into delta Z is equal to delta Z into rho into G, where we have used Taylor series expansion that P at Z plus delta Z is the same as P at Z plus del P del Z at Z times delta Z plus order delta Z square. So this is the first order term because it depends on delta Z. This is the 0th order term because this depends on delta Z raised to 0. Okay, so we have this, which is the same as saying, this is the same as saying del P del Z minus del P del Z is equal to rho into G, which implies P2 minus P1 is equal to rho G Z1 minus Z2. So we have essentially integrated this in space over Z, assuming that rho remains constant for the fluid. So this is the condition for equilibrium of a fluid. Okay, so if we have held this block in place P2 minus P1 at any 2 points in the fluid is governed by this. Okay, so P2 minus P1 is governed by this. Let's copy this figure for our reference again. Okay, so then for the equilibrium of this block, we have P at Z multiplied by the area of the block minus P at Z plus B times the area of the block minus rho of the object G times the volume of the block, which is A into B, because the area multiplied by the height of the block is equal to the volume, plus any holding force. Let's say there's a holding force in the positive direction. So at equilibrium all this must be 0. But now we have just seen that from this expression P at Z plus B minus P at Z is equal to rho into G into, now look, Z1 is P1, so this will be Z minus Z2 is the same as P2, which is Z plus B, minus of Z plus B. This is equal to minus rho G into B. So these two terms become minus rho G B times A so this is P at Z plus B minus P at Z. This is P of Z minus P of Z plus B, so this becomes plus. Okay, please note this is minus, so this becomes plus because this Z is here. Minus rho 0 G B A plus FH is equal to 0. So FH is equal to rho 0 minus rho G B times A. So this is also equivalent to rho 0 minus rho times G into volume. So the holding force required to hold the block, holding force, if rho 0 is less than rho, and FH is negative, which means that the direction of FH, as we have assumed here to be positive, will actually be negative. Okay, and it is equal to the difference in the densities between the block and the fluid times the gravitation times the volume. Okay, so this is quite obvious. As a homework, I ask you to derive the buoyancy of a sphere. Imagine a sphere like this having a density rho object. Now establish what is the holding force on this object. Okay, we know that pressure acts in the normal direction uniformly on the sphere, and the problem is axisymmetric because there is no phi dependence on the problem. So if we call this as theta, the problem only depends on theta and not phi. Phi is the polar angle. So let's say the radius is r. So please derive an expression for this, and you have to make use of the elementary formula that minus del p del z is rho g. This is from the statics of the fluid. And so P at any location minus P at some other reference location is equal to rho G Z1 minus Z2. So you have to make use of this fact to obtain the net force because of the pressure distribution. So the pressure here will be lower than the pressure here. The pressure at this larger depth will be larger than the pressure over here. So there will be a net force upwards, and if the body is light and the body tries to go up, so rho 0 if it is less than the rho. So please try to find out the expression. Okay.